Uh, yes, it sounds a bit strange, quantifying academic careers. I believe we need to know more and more. And the global age here in this title, and how to quantify academic careers in the global age. Global age means more and more data, digital data sets, big data, etc., etc. Now, there are certainly strengths and weaknesses of using these new data, and I'll be talking about it well in more detail today. So, well, academic careers and digital traces, meaning we all leave digital traces behind us. Well, in publications. So digital traces means our publications and metadata from the publications. Structured big data. In our case, in my case, that would be Scopus raw data set. What can we explore? I'll be stressing the power of academic surveys, their limitations, but also their power. I will describe our methodology right now in Poznan, and I will give two examples from most recent research. One is global women in science, or especially young women in science, and the other is persistence in high productivity, like today, highly productive, perhaps always, in the past, highly productive. So there will be global example and national example with global data. Finally, limitations of global data sets and, well, takeaway messages and conclusions. This is the colorful picture, which I love. This is my Poznan team, the academic profession, global academic profession research. And today I'll be describing research with Dr. Wojciech Roszka on the right. You see, I have the square around him, and Łukasz Szymula, my doctoral student, that'll be the global study. I have a generally fantastic team. I'll not be talking about research from the past few years, where I focused on mostly about women in science, men-women collaboration, the various dimensions of gender gaps, etc., etc. I'll focus only on current, really ongoing research, where I'm combining national data, biographical data, and big data from Scopus. You can see here 3 examples. The first will be available from higher education on Monday. The second is revised currently for studies in higher education, and the last one is revised for quantitative science studies. Just 3 slides of very brief introduction about these digital traces in academic profession studies. Well, we all leave traces in our index publications. And my strong feeling is that if we want to study academic profession globally, there are no other reliable sources, no reliable traces, just global data sets. So what we can trace academics over time. So we can change publications over time, which is clearly longitudinal approach. And we can use the cross-sectional approach, like 1 year or year by year. We can study countries, but also we can study individuals. What I'm doing, basically, studying individual academics. We can study teams. I was studying male teams, male-female teams, and the female teams. We can also study, well, juniors and seniors, disciplines, certainly. And what is especially important is the precision. We can measure, again, quantify the academic profession with ever more precisions, with limitations. And I will discuss the limitations clearly later on today. So, structured big data and academic profession studies. Who creates, collects, and owns the data? It's companies and governments. So this type of data are not really designed by us researchers, and are not designed to be used by us academics. It's important to remember, it's not self-produced data like the data we produce in academic surveys. They are being produced around, and we want to have access to them. And there's an enormous amount of data today compared with 5 or 10 years ago, just enormous amount. It's unbelievable. What can we do with the data? It's unbelievable what is included in those digital traces of our, well, I would say of our work, that is in our publications. So We can extract information about us academics from millions of cells using cloud-based data sets. What we are doing here, just to give you one example, as a teaser, we used 1.4 billion cited references just to define every single scientist discipline in our data set. So it's really, well, I would say the data are huge. And my message is that this type of big data increases, I would say dramatically, our insight into the academic profession. I would say even more, others are doing it, not exactly higher education researchers, but for instance, computer scientists are doing it perhaps not routinely, but they do it from time to time. What can be explored through these structured big data? Well, certainly traditional issues like research productivity by various types, say top journals versus all journals, collaboration also by various types, team size, average team size, international collaboration, but also, which I also mentioned here, solo research. I studied gender solo research gap, but also same-sex collaboration or mixed-sex collaboration, all types of collaborations. So we can study scholarly impact through citations, we can study authorship types, etc. I put it here that basically we can study all scholarly activities recorded in publication metadata, and we can study this metadata by gender. It's enormously important. We finally see not scientists, but we finally see men and women scientists, which was not possible, say, a decade ago, just impossible. We can study all those dimensions of academic work by age or age cohorts, which I will discuss later on today, by academic seniority, by disciplines, enormously important disciplines. We differ and we work in tribes which are disciplinarily located. And we can do it both statically, like 1 year, last year, or dynamically, 2 decades, 3 decades. This is what we are doing here in Poznan. The rationale. What was the rationale of me taking care of big data? You may not know, but I spent about a decade working with academic surveys, global academic surveys, European academic surveys, and the national academic surveys. A decade. Also, my Routledge book is based on survey designs and survey data. And I saw a number of limitations, and I have a number of reservations. That's why I moved somehow to big data. So just to give you an example, you have, say, 1,200 observations per country routinely, like 1,000, 1,200 per country. And then you want to study, for instance, the scientists or academics by discipline, or by age, or by seniority, or by gender. And finally, your sample goes down from 1,200 to a few dozens. And that's the point. With low numbers, with small samples, you can't do much. You can do something, and we did it for decades. I also did it for a decade, and we did it for half a century or more in higher education studies. But there are limitations. Just this red example. Just have a look. If you want to study highly productive young academics under 40, working in STEM disciplines, in special type of institutions, research intensive, by gender, male and female, your sample goes down to a few dozens. And that's the point. Global surveys can sell this issue, but generally, this is dissatisfaction, which I feel with working with surveys. But I will show in a moment, some dimensions can be studied only and exclusively through surveys. So the question is, what can be collected only through surveys? Perfect example, there is continuing power of academic surveys. We can't study through any other data than survey-based behaviors, academic behaviors, attitudes, and perceptions. It will continue forever. And I'm involved in this type of research. I'm doing a survey study of 100,000 Polish academics right now, as we speak, this year. So I know it's important. But I know it's important to combine different types of data. So survey-based, national, and global, bibliometrics-based, etc., etc. So have a look. Rate your own salary. You can do it from big data, or describe your working conditions, working conditions, or if we think of academic productivity, marriage, children, and parental leaves, almost impossible. I would say impossible to do it without any other data than survey data. But also academic freedom and restrictions, or leaving, considering changing a job, leaving higher education sector. These are all typical questions from global or national academic surveys. We know we can't do it in any other way. But what is our approach when we have access to digital databases? What do we think here in Poznan? First, we believe in a need of a major transition from publications, which is a typical bibliometric approach, to scholars, which is an approach of academic profession studies. So think, when you use global metadata and you focus on scholars, it's another dimension of global academic profession studies. That's something new which has to be used, I believe. So we use national level data, and we use big data. Our data source is Scopus raw data. But we also have Web of Science, core collection, raw data, different types of data sets. But today I'll be talking about Scopus raw data only. So our focus in this research I mentioned is scientists or academics and their individual attributes, and not really publications. I'm talking about academics and their attributes, which is a typical approach of academic profession studies or academic career studies. Why now? Well, why now? Access. We have access to digital databases, which were not available a decade ago, or not available to many of us or most of us. So we have national databases like national registries of scientists. We have global databases like Scopus. We have commercial databases like, again, Scopus, and non-commercial like Polish Registry of Scientists. So governments and companies, the data are around us. They are bibliometric, they are workforce data, labor force data. They're all around. You can see a couple of sources here. Well, how we construct the sample in our ongoing global studies. When I'm saying global, it's actually OECD, 38 countries. How we work with this enormous universe of the Scopus publishing, of all publications in Scopus. We just cut this publishing universe into slices, and we go down from millions, from dozens of millions to a few millions of academics. So we have to determine gender, we have to determine discipline for everyone, we have to determine country, we have to determine, well, we call it non-occasional status. We focus on academics who have at least 3 publications, 3 or more. It's arbitrary, but it's very useful. We have to determine academic age. So when you look at all those determinations, we go down from 43 million scientists available in Scopus to 4.3 million, which is our basic database at the moment. We have to define all of those 5 dimensions to have individual attributes characterizing individuals. We need clear gender, binary, men or women. We need clear discipline. In this research today, we have only STEM disciplines for a number of reasons: science, technology, engineering, mathematics, medicine. We need country, just one country. We need this non-occasional status, like 3 papers at least. And we need academic age for various types of analysis. So we need a person, academic, with those types of attributes clearly defined. Now, I'll give you 2 examples. One will be global and another will be national with global data. What we studied recently, we studied changing demographics of global scientific workforce. We wanted to know, is there a real inflow of young women to science in STEM globally in the past decade? We can't find this type of data. Young academics or very young academics or female young academics. We can't find this type of data in OECD or UNESCO or Eurostat statistics. We can find something for some countries, but globally, it's absolutely impossible to explore this type of demographic questions. Are we graying as the academic profession right now? Are we having more and more female academics around? So we have anecdotal knowledge, but basically we don't have data-driven knowledge. So this is what we are doing. We try to move beyond traditional statistics of the OECD, UNESCO, also of national statistical offices, which provide data to global statistical offices. Just 2 or 3 snapshots of the results. We have 1 year here, and we have scientists divided by disciplines and divided by cohorts. From very young cohorts, 5 and less years, you can see, to young cohorts, up and up and up to very old cohorts. And we know that there are more women in some areas and fewer women in other areas, and there are areas in which there are no changes at all over time. We know it, but it's basically anecdotal knowledge. And here we present, or I present the global picture. Yeah, 1.5 million scientists. What is immediately clear? There are 4 areas in which I would say nothing changes. So with subsequent generations, the share of women, which is dark blue, is just the same. Look at mathematics, math, or physics and astronomy. You can see that no matter which age cohort today we take, the share of female is just the same. Think of computing on the right. The share of female, about 20%, it's just more or less the same. So we can imagine that these are separate disciplines from all others. Think of medical sciences. There are more young women than young men today. There are 6 disciplines in which there are really the majority of young scientists are women, and this is something we expect, but we really don't know. Here we looked at the very young and young academics. Here, scientists, not really academics, but we can drive it down to academics. Totally, about half of young academics are female. This is surprising. But in medical sciences, it's more than a half. In biochemistry, it's more than a half. We are disciplinary tribes in higher education, and we differ by disciplines. Again, physics, 20%, computing, 20%, nothing changes, I would say. And we wanted to know from a larger perspective, like 3 decades, are things changing in the past 3 decades? We took 4.3 million scientists in those STEM areas, and we did a logistic regression of the changing percentage of women in particular disciplines. You see the slopes are different. Look at medicine. There were a lot of women 30 years ago. The percentage was high, and it's very high today. Look at immo, which is immunology. Also, a lot 30 years ago, high percentage, today very high percentage. And look at physics, mathematics, the big 4. I would say the changes are slow. And when we look at the details, when the parity could be achieved, it's a rhetorical question. It's a hypothetical approach, just an exercise. But when we could expect 50-50 parity between male and females in particular disciplines. It's in 100 years in the big 4. Mathematics, computing, physics, astronomy, engineering, more than 100 years. But when you look at young women and young men, parity is already achieved. There are 6 disciplines in which there are already more women than men. And remember, I'm talking about only STEM disciplines. I'm not talking about social sciences or humanities, where it is more obvious there are more and more women. I'm talking about STEM disciplines. So this is something we expected, but actually it was not calculated. It was not really described in detail. And this is a somehow global picture. It's really OECD, which is 38 countries, but it's more than 60% of global academic production today. Why we don't do global study, a truly global, like 180 countries? Because of the issues. issues with gender, which is enormously complicated for China or Vietnam, or the issues of small contribution to global science. There are some countries with very small numbers of publications. Generally, for us here, OECD works better than the truly global approach. And so we had a teaser of a global study. Now we have a teaser of a national study, a Polish study driven, or I would say driven by global data sets. So we took Polish scientists, but we use global data for them. So a simple question: once highly productive, forever highly productive. We took full professors, 2,300, and we look at their lifetime publishing history, 40 years of their publishing. And we were thinking, okay, if they are so productive today and they belong to top productivity class, perhaps they have been also highly productive before as associate professors or as assistant professors 20 or 40 years ago. I would say this is the type of question which can never be answered without global data, because it's the only type of data which gives you, in our case, it was almost 1 million publications, which gives you 50 years of articles year by year. So this is an example how global data can enhance national level studies. Well, what we do, it's certainly not bibliometric in nature. I call it academic profession studies, but we could also call it quantitative science studies referred to academic profession, or whatever. The label is not important. I would say the source of data is important, the approach is important. So what was not possible in our case to do without Scopus data, without this big data? In our Polish case, a simple Polish case, which will be available next week, basically on Monday or Tuesday, in higher education, changing productivity lifetime by classes. First, it was not possible to define disciplines for every person, just impossible in the Polish case. It was not possible to measure productivity by prestige of journals, just impossible. It was not possible to link every single article to 3 stages of academic careers. There's assistant professors, associate professors, and full professors. We could do it only with Scopus data. Finally, without this big data, we couldn't establish academic age for full professors. We had biological age, but academic age, the age of the first publication, the time from first publication to today could not be established, and we needed it in our regression models. So you can see how about 1 million publications helped us to produce a story about 2,000 Polish full professors today. We look retrospectively back into their productivity. And this is the picture. I don't want to say too much, but just one remark. We have assistant professors in first column, associate professors in second column, in full professors in the third column, and we see the classes of productivity, top, middle, and bottom. Some people are always in top classes, some people are always in bottom classes, and our question was how often it happens. And it looks like when you look at transitions, say between the first and the second column, you can see that top to top transition for all disciplines combined is more than 50%. One stop, always top. Not always, but very often top. But it's from the other perspective, also those scientists who are classified bottom class at the level of assistant professors, later on were bottom class associate professors, and later on finally were bottom class full professors. So big data allowed us to study 40 years of changing productivity classes. We're not really interested in changing numbers, because the numbers increase all the time. All of us produce more and more publications and index publications 3 decades ago, 2 decades ago, and today. So we knew what the picture would be. We needed classes. So top 20%, middle 60%, and bottom 20%, and how people navigate between those productivity classes over lifetimes, over 40 years, across 14 disciplines. You can see it here by discipline. In every discipline, the share of those moving from top to top is more than 50%. Sometimes it's 70%, like in mathematics. And also, when you think of those jumpers up, those who move over their lifetime from bottom to the top of productivity, it's a rare, very rare, well, academic species. You see those very small ascending lines moving from bottom to top. They are so small, sometimes are not even visible. So jumping up is enormously difficult. And we know it from this small-scale national study, but we do it also at the moment, as we speak, at the OECD level, at the OECD scale, from about 4 million of scientists, exactly parallel study. So finally, global data sets, they have limitations, and we know it. So we know we can do cross-sectional studies like 1 year and longitudinal studies like 2 decades. We know it, but still there is some methodological price you have to pay. There's no free lunch, and accessing new data, using new data, we have to assess this price we have to pay. I will assess it in the next slide, but I will tell you at the moment that it's useful to treat, there's bibliometric data sets, Web of Science, OpenAlex, Scopus, as structured, sometimes very nicely curated, structured big data. It helps to think of bibliometric data if you call them big data and use big data analytics, big data literature. It's enormously useful. Is it really big? I would say the data are large and they are very complex. We are working right now in our OECD data set with 1.5 terabyte of data. It's cloud only work. It's just impossible to use it in any other way on just our computers. So we have access costs, running costs. It also means teamwork only. I would say solo authorship is no longer possible. I was raised in the cult of solo authorship, and most of my work was solo research until a few years ago. And now it's exclusively or almost exclusively teamwork and multi-authored because of this interdisciplinarity which is needed. There are limitations which we know, limitations about bibliometric data. English, yes, in English mostly. STEM focus, yes, true. Anglo-Saxon bias, true. But there are also new limitations which we discovered in our work, a new limitation we discovered in our work. And that's what just one slide about these limitations we had to tackle. There are problems with gender determination. There are always gender unknown cases, always. From country to country, the shares of these gender unknown cases are different, and we somehow have to accept it. Or we do a parallel studies using these gender unknown cases, which is a bit complicated. Now, we use commercial definition of disciplines, and that's also a price. There's a richness of nationally defined disciplines, say Polish disciplines, fantastic, but globally with big data, we have to use a joint classification. I would say it's a price to be paid. Then country affiliation, just one. We forget about migration histories, just one country. Then the status, why 3 articles per person or more. It's exclusionary and it's arbitrary, but still we know it works. We tried 2, we tried 5. I would say 3 is best. Determining academic age, we know that patterns change over time. People in old times, say 3 decades ago, were beginning to publish later on than young people today. So we know all those issues and we have to deal with them. Finally, perhaps most importantly, most traditional statistical assumptions don't hold in big data sets. As you can imagine, in big data, we work with populations. For instance, all Polish scientists were visible internationally, publishing internationally in, say, 16 STEM disciplines. It's population, it's not a sample. So all those traditional generalizations from samples to populations just doesn't work. We need to stick to big data analytics. And that's why we need teams, we need interdisciplinarity, we need colleagues from, well, different areas like computing sciences, statistics, or big data analytics. That's one of the prices to be paid. Takeaway messages and conclusions. Well, you could see in study 2, which was a Polish study, that it's possible to merge bibliometric data, this 1 million publications, with administrative and biographical national data, like National Registry of Scientists. You can do this. But some data are available only in these registries and only in some countries. Think of date of birth. It's really not available globally. So we use academic age. Think of ranks or degrees. Well, in Poland available, for some countries available, like the UK, like the US or Norway or Italy, but not globally. So in global studies, as opposed to national studies, we use proxies, we use thresholds, we use inferences. For instance, we use biological age. We don't use biological age, but we use professional age or academic age. We don't use, well, our gender is inferred, so to speak. There are different probability thresholds. We have to infer it. So it's not exactly 100% male, female. The threshold probability say 0.85 or 0.9. So it's as if men and women. Well, we use academic ranks through some proxies. So we can have length in service rather than, say, assistant professors. Globally, we don't have assistant professors. We have just length in service, and so it's just a proxy. In global studies, we have publishing only scientists, which is another limitation. Publishing only, not all, but publishing only. In registers, we have all. In big data, we have publishing only. If you don't publish, you don't exist in global data sets. Nationally, we have real scientists. And in big data, we have Scopus offer IDs. It's not exactly the same. Scopus offer IDs. And finally, we have near perfect national data, like registries, near perfect or perfect. And we have some inferred data or proxies from big data. All those costs and limitations needs to be assessed carefully, and then decision is taken. We do it, or we didn't do it. Generally, we do it, but we describe the limitations. And summary. Well, what was the dissatisfaction? Dissatisfaction for us, was the small observation numbers in traditional surveys. We can't do much with small numbers, and we can't do nothing globally. We can't do anything globally. And from cross-national perspectives, we can do only something. Because as you remember, when we cut the data by gender, by discipline, by age, by whatever, our numbers are too small to have significantly or interesting results. My answer is, these are new data, complementary data. So we don't never get rid of academic surveys and interviews, but we complement these data sources with big data. And big data can be used nationally, as I show in study 2. They can be used cross-national, like 2 countries, and also globally in this OECD type of research I told you about. Certainly, there are limitations, and there's repurposing needed. Data from governments, data from companies like Scopus or Web of Science need to be repurposed. They were not produced for us. They were produced for companies to be sold. We are scientists, academics, and we need to first most often buy them or have access to them and then repurpose them. Still, the amount of data is enormously, and it's very promising. Amount of data is promising. Also, the longitudinal character of data is promising. We can study academics over decades, year by year, like in the Polish case, 40 years of academic lives were studied using Polish and big data. So we can see imperceptible patterns we didn't even think about. So we could, in the Polish case, we could have expected that some people will always be top productive. but we weren't able to say it using data from 40 years. Now we can. So there are some imperceptible patterns become visible. Finally, I would say that we can sharpen our insight into the academic profession. I would say some people do it globally. There are some teams globally which think about the academic profession, but they don't have the background and the theoretical, background to think about the profession. They are computer scientists. They do a lot of fantastic data analysis. But still, if it comes from us, higher education researchers, I would say it's much more promising. So finally, we have more precision, more detail, just remarkable detail. And at the moment, this is the last sentence, at the moment, we are finalizing like 3-4 large analysis. One is about the graying of the academic profession globally. The graying, are we graying? We know we are, but how we can show it. Another is the answering to the question, are men oversighting themselves globally compared with women who are undersighting themselves, with a lot of implications for gender gap in promotion, gender gap in access to competitive research funding, etc., etc. So we started this type of research about 2 years ago. First publications are emergent. I would say first as preprints, but finally also as papers. And the story goes on. Thank you so much. If you have any questions, we have 20 minutes left. You can contact me also through Twitter. I'm very avid user of Twitter by email, and I'm finishing showing the slide, and Anatoly will run the rest of the show, please.
Thank you very much, Marek. I certainly look forward to reading your newest paper in higher education, and the talk was fascinating. So I look forward to questions and comments, and I see the hand risen by my colleague, Professor Chiu-Min. Meanwhile, just use please chat, or if you want to ask a question, use the hand in the reactions button on your Zoom. Min, please, your time, if you can please ask your question.
Thank you for an interesting talk, Professor Marek Kwiek. I wrote my question in the chat window. I'm sorry, my camera doesn't seem to be working, so I can't turn it on. So I was wondering, which statistical analyses did you use? Like, did you use multi-level cross-classification analysis, multi-level diffusion analysis, or something else?
Yeah, great question. The major issue is this passage from samples to basically populations. That's a major issue. I will work in our research with populations. In this global study, we work with populations. We don't expect those generalizations from samples to populations. So our approaches are taken much more from big data analytics than from traditional statistics. When we focus on smaller samples, like the Polish case, highly productive academics, top productive class, our approach was through regression analysis. So the question was, what makes current highly productive professors so productive? So what increases the odds of entering this class? So traditional approach, odds ratio estimates of entering the class. So sometimes we combine traditional methods. Sometimes we use approaches available only in big data analytics.
So if you're interested, there are ways of using these more sophisticated analyses. So for instance, diffusion analysis. Let's take a question about which theories are most influential in discipline. Multi-level diffusion analysis will let you know what affects the likelihood the ideas will spread or be cited by other people. So if you're interested, we can chat more.
Yeah, I would definitely recommend I probably put you in touch Professor Chiu. He does some amazing research in analytics using statistical data and machines to understand better this kind of the depth of statistical analysis. So,
well, actually, just let me add one more comment. So another thing to consider is to use like artificial intelligence to like look at the text, not just like the metadata, but also like the actual abstract, for instance, or the entire paper.
Yeah, definitely. Yeah, we work at the moment at the level of scientists or academics. So we focus on people and their attributes, academics and their attributes, rather than papers and their attributes, including what is inside papers or what is inside abstracts. So it's slightly different approach. Our focus is coming from academic profession studies rather than, say, well, traditional computer sciences or bibliometrics where papers rule. In our case, academics rule, not papers.
Thank you.
You're welcome.
all right. Any questions? Can I probably, since I don't see any questions at the moment, can I ask you about your choice of STEM? I remember I was trying to understand why STEM is priority. You emphasize research in science, and I sometimes think that social science probably difficult to quantify, or is it because of politics, or is it policies or data sets not being perfect as much as they are in the journals in natural sciences, so these kind of harder sciences, let us say? So can you please tell me?
Definitely, Anatoly. That's a fundamental question. Before we moved on to STEM disciplines only, we did a lot of studies focused in Poland. For instance, we were studying academic age and its biological age and its correlation with academic age. And we were thinking how it works for STEM sciences and how it works for other areas. Generally, I would say that the big data that we use were created for STEM sciences. Only later on, social sciences and humanities were being added, and they're continuously being added. But still, if you look at social scientists and humanists, the majority of their publications, in most cases, are not indexed. So we wanted somehow to avoid the big fundamental issue and criticism of bibliometrics and bibliometric type data, in which we all know that social sciences are underrepresented and humanities are underrepresented in both Web of Science and in Scopus. We just know it. So it's a choice. Whether you want to combine almost ideal data, like in the hard sciences, Web of Science or Scopus data are almost ideal, and combine them with far from perfect data about social sciences. And then the whole picture gets somehow ruined because you have very good data and very limited data. I believe it's better to focus on what is very good and do social sciences separately. But again, there are so many discussions in the past 2 decades regarding the underrepresentation of social sciences and humanities in Scopus, and especially in Web of Science, that it's probably useless to think that we are doing something sensible, something convincing and reasonable when we focus on, well, us. Well, I'm also a social scientist. You are a social scientist. Yeah, we are part of. Some of us are also humanists. We know it doesn't work. So I'm always saying I'm cutting the Scopus universe first into STEM, non-STEM, or social sciences, humanities areas, and then I stay with STEM. When you look at the founding fathers of academic profession studies, or founding fathers of sociology of science, like say Robert K. Merton or the Coles brothers or Harriet Zuckerman, they were all working with the data from the sometimes 50s, 60s, 70s, with this type of data about hard sciences. It's somehow more applicable from the very beginning. They have very small samples, interviews, publishing data, but still they had astronomers, they have mathematicians followed over cohorts. So it's very close to my mind. I don't have this feeling I'm reducing science to something, because it's been done in the past half a century by almost everyone. But it's a pity. Certainly, it's a great pity. Nationally, we can work with humanities, social sciences, because we have national data in our languages, like Polish. We have 1 million Polish publications, including social science, but it's a different database. There's no prestige. There is no real metadata of the kind we get from Scopus. So I regret, it's a great pity, but even if there are more and more social scientists in the database, the past is not included, the past 30 years. So I don't really believe we can do this type of research using big data today, but we can do it using surveys. So, this is type of work we can do even with global surveys, but it's a pity. Yes, I agree.
Very interesting. Thank you. So I see two hands risen there by Mulat Goshu and Denis Sveredenko. Mulat.
Okay, thank you very much, Professor. It was a very interesting presentation. The question that I have is promotions from one academic rank to the next academic rank. It varies from countries to countries and even from one institution to another institution. So how it is possible to establish equivalence among academic ranks, assistant professor, associate professor, professor, in just when we use the global data, meaning just how can we make that equivalence of academic ranks across different countries and different institutions?
Yes,
thank you very much.
It is a fundamental question. Thanks so much. Indeed, it really hits the mark, because we did the Polish study and we had really assistant, associate, full professors with dates, date of doctoral degree, habilitation degree, professorship title, perfect data set, national. And then, well, we do it globally. Oh, we were thinking for a long time, can it be done? And actually we are finishing a huge study in which we made the following trick. Okay, we have in Poland full professors. Globally, what is the equivalent? The equivalent is those who have been working in science for a long time. They can be full professor or they can't. It's hard to say. But globally, if you take many countries, you don't have degrees and you don't have ranks. It's true. It's impossible to have ranks. But you have length in service. So we said, okay, the equivalence of those full professors in a global case could be those working for a very long time in science. Most of them could be full professors. It doesn't matter. Their seniority is equivalent to Polish full professor status. And then we moved back to those working, well, the medium time, and those beginning to work, like those equivalents to, say, assistant and associate professor. It's a proxy. But I would say, again, working with the data is full with proxies. If you explain the proxy properly, and if you say it's possible for Poland, it's possible, the ranks, it's the rank idea. It's possible for Norway, it's possible for Italy. And if you have access and money for academic analytics, you can do it in the US. You pay for academic analytics, you have the ranks. But globally, no data, even if you want to pay for it. So we use proxies. I believe at every step, we need to use proxies if you want to make sure that there is some reasonable result from our studies. Otherwise, we come back to our local national studies, which is perfect. We love it, we do it, okay. But globally, proxies everywhere, inferring something everywhere. There is some degree of error, always, degree of probability, but I believe it's worth it. Even if these are big pictures, I believe it's worth to do it. Unless someone says, Marek, you're wrong. It's absolutely non-acceptable. And I would say there are no other data sets, so we don't do it. The answer is we do based on what we have. We have 2 global data sets, like 3 global data sets with some data, with some access if we pay for it, or we have, working agreements with like Elsevier or Clarivate. We can do it. With many limitations, we can. Running costs, costs per year, a lot of costs, but still it's possible to do it. But exactly ranks, no, only some proxies.
Thank you.
Thank you. Thank you very much.
Dennis, please.
Thanks a lot, Professor Kwiek, for your interesting presentation. My speech is not a kind of wide question, it's a kind of comment. I think that taking into account the possibilities of your methodology, it could be interesting for the nearest future to use this approach, for example, to estimate the academic losses of Ukraine, taking into account the migration processes following the Russian Federation aggression. And as we know, the most of migrated citizens are women, and 70% of them are women with high education degree, and a lot of government agencies says about the big intellectual and academic loss for Ukrainian science and for Ukrainian society. So we can estimate what kind of gender situation in publication we had in Ukraine. What about after the beginning of Russian invasion? What situation is after the 1 year of invasion, and also to see what gender situation happens and maybe what countries raised the intellectual and academic potential and publication activities through this lens. So maybe you have any idea,
Yes.
the kind of theory.
I absolutely agree with it, but we need like a few years of data. So first, Ukraine is not enormously, massively present in big data sets, but it is present. So it's possible to use big data. We need a couple of years to see who moved where, or who was publishing and was young and stopped publishing. Well, using some proxies, it's possible to say that, for instance, 30% of academics, male academics, slowed down in publishing or stopped publishing at all. And you can compare male and female science. I don't believe in numbers. I believe in proportions. So you can compare male and female participation in global science prior to the war, 10 years before the war, year by year, and then after the war. You can't do it in 1 year because you need, again, our traces are publications. So we need to wait, I would say 5 years. I would say even 5 years. Sorry to disappoint you, absolutely. But after 5 years, you know the details. You have all the traces. Okay, lost generation, lost half generations, more women than men in some areas, not in social sciences, whatever. It's all possible, but we can't do it from my perspective, which is, traces in big data databases. You can't do it now, but in 5 years, it would be perfectly possible to assess the impact. Like you assess the impact of Chinese, broken Chinese, Chinese-American collaboration. You see the details, or Russian-American collaboration. You begin to see the details in big data. With Ukraine, which is more specific with male and female and, life histories. It's not migration for academic work, it's migration for life. So it's different type of migration. You need more years to assess the impact, but I would say it's perfectly possible.
Thank you so much, and great question and great answers. We've reached our time limit, so I would like to thank Professor Kwiek for this engaging talk today. So we all look forward to your further studies and publications. Really exciting work. So wish you good luck with and you and your team in general. And we look forward to seeing you back to our community one day, and where you can share more insights with us in the future. So thank you so much, Marek. It was really a very, very exciting time. Thank you.
Yeah, thank you so much for spending this hour with me. It was a great pleasure. And Natalie, thanks for the invitation, and we are in touch. Thanks so much.